Okay, so here is the second part of this lecture, looking at how we actually do the hypothesis test and what that means for this content. So when we're looking at the general hypothesis test procedure, it's a 7-step process. So step 1 is know your parameter. And so you want to look at the parameter of interest. So this might be a mean, this might be a variance. This could be a proportion. Most always we're going to be looking at means in this case. Then you state the null hypothesis. You want to know what is the null hypothesis because you want to know what are you comparing to. So HO. That is what we want to understand. After you have a null hypothesis, you need an alternative hypothesis. And remember the alternative hypothesis, H1, could be a couple things. It could be not equal, and that's for a two-sided, or it could be less than or greater than for a one-sided hypothesis test. So HO is your null hypothesis. H1 can either be not equal for two-sided or less than or greater than for one-sided. Then you want to know your test statistic. And the test statistic is going to be given to you. So this is what we are comparing a p-value to. And so this is given. And it's almost always given as an alpha equal to a certain number. The most common test statistics are going to be 0.1, 0.05, and 0.01. Now, if you remember from chapter 8, what are we looking at? We're saying a 90% confidence interval, a 95% confidence interval, a 99% confidence interval. That's what we're looking at, right? So that same test statistic for two-sided test or a one-sided test, we're looking at that tail to say how much of the population is going to fall within the curve and how much is in the tail. So then we need to know why we are rejecting the null hypothesis. What is the criterion for rejecting the null hypothesis? And so again, this is going to be given to us. So if we have a significance value equal to 0.05, if your test statistic that you calculate is less than or greater than 0.05, you're either going to accept or reject accordingly. So knowing the test statistic and then the criteria, those two go together. Then you do the computation. And so this is the computation. Most frequently, we're going to be looking at confidence intervals. So that's one thing that we look at a lot, confidence intervals. We might look at type 1 error. We might look at type 2 error. We might look at sample size. We might look at p-values. But we're going to do some sort of calculation to determine if we can compare the data that's been collected, the mean, the variance, the proportion, to the null hypothesis and confirm, either accept or reject our hypothesis. And so that's the last step, is your conclusion. And this is what makes this class more than a math class, because you're making a decision to either accept or reject. And this is where in the real world you would be determining like if your experiment was correct, if one opportunity was better than another, if you had two products and you were comparing and saying, does one product work as well as the other product? The answer might be yes, it might be no. So in all of our questions that we're going to do in homework, on quizzes, for exams, everything's going to be focused on this idea that we're either going to accept or reject the null hypothesis. And that leads us to a decision about what we need to do. So let's give an example of this. Now, when we have the mean and the variance known, we're looking at a normal distribution. And so our null hypothesis is always going to be that the mean is equal to some value. And so we're going to say our null hypothesis is always comparing a known mean to the information that we've collected in our sample. That's what we're looking at. Our test statistic for a mean and variance known is always going to be our z-test statistic. And so that's going to be the sample mean minus the given mean of interest divided by the standard deviation over the square root of n. And so that test statistic is always going to be what we're looking at. And so when we have a two-sided, and this box here is on the notes, you should be able to see it better on your computer, but it's also available in your textbook. Two-sided, when we have an alternative hypothesis that the mean of the population is not represented by the mean, then the probability above and below is going to be equal to p is equal to 2 times 1 minus the z statistic of our calculated z naught. Now, what does that tell us? Well, that tells us that's the same thing that we were doing for calculating those p-values, right? And that's what we were seeing in setting up our confidence intervals. So this should be really, really familiar. For our one-sided, we have two different ways of looking at this. For saying that we have a measured mean that is greater than mu naught means that the probability is equal to 1 minus the z-test statistic. And for the probability that our mean is less than mu naught, we're looking at just the test statistic itself. So what does that remind us of? Again, that should remind you of chapter 8 when we were talking about how if we're looking at the upper tail or the lower tail of our confidence interval and how we calculated those p-values. So the p-values in those criterion are all what we're looking at to try to make a determination if we accept or reject. And this box here is something really important for you to have for all of our tests, our z-test, our t-tests. That's going to be really important for you for all of the future tests that we're doing for the coming chapters. So definitely flag this page in your textbook. So what's an example? What would this actually look like? So this tells us that the specifications require that the mean burning rate has to be 50 centimeters per second with a standard deviation of 2 centimeters per second. We've got a significance level of 0.05 and there's 25 samples and our sample average was 51.3. So what can we tell us? Well, we're looking at the mean. So our parameter interest is the mean, as it will typically be. And so our H naught, our null hypothesis, is that the mean is equal to 50, because that's what we actually want to have happen. We want the mean to be equal to 50. The alternative hypothesis is that the mean is not equal to 50. And so in this case, we have a two-sided hypothesis test, equal to 50 or not equal to 50. And because we know that we're looking at a normal distribution that has been given to us, that we are going to use our z-test statistic, and it is equal to the sample mean minus that mu naught divided by the standard deviation over the square root of n. And we're going to calculate that. Now, that's our test statistic, and we can go ahead and look at what that is. That is, for this case, 51.3, because that was given as our x bar. X bar is equal to 51.3. Sigma is 2, n is 25. Those are all given statements. And our alpha is equal to 0.05. And so with all those given statements, we have 51 minus 50 divided by 2 over the square root of 25. And that math is equal to 3.25. So that's our z-test statistic. Well, what do we know about our rejection region? We know that we want to reject HO if P is less than 0.05. So if P is less than 0.05, we are going to reject it. And so for a uh, 0.05 and alpha over 2, we would look at z of alpha over 2 is equal to z of 0.05 over 2, and that means a z of 0.00025, and we know that to already be 1.96. And so we're going to look at our calculated z value. Our z naught was 3.25, and so we need to convert that into an actual p value. So then p is equal to 2 times 1 minus your z statistic for 3.25. And in this case, that's equal to 2 times 1 minus 0.9994. And so that's equal to 2 times 0.006, and that is equal to 0.0012. So now we're going to check. 0.0012 is less than 0.05. That's true, which means we are going to reject the null hypothesis. So let me move this up since I've been writing off your screen and just go through it briefly. We know we're given 50. Alternative hypothesis is not 50. We calculate our z statistic. We calculate the p-value for our z statistic. Our p-value for our z statistic was 3.25, which gave us a 0.994. 1 minus that is 0.006, multiplied by 2 is 0.0012, and that in fact is less than 0.05, which means that that statement is true and we need to reject H naught. So our null hypothesis has been rejected. What does that actually mean? It means that right now, based on the sample that we were given, based on that sample mean of 51.3 with 25 samples and a standard deviation of 2, you are not meeting the required mean. So the sample taken from this product says that we are not meeting the required mean. That's the actual decision. That's the conclusion, that based on the sample that we have taken, this does not meet the product requirements. So how do we relate this to our type 2 error? Our type 2 error we first calculated as being a calculation looking at the difference between a true mean that we think is in existence compared to an actual true mean. So we said, we're working on the assumption that our mean is 70, but it's actually 73. What's the likelihood that we would reject that or accept it even though we should reject it? And so we're able to look and say that we can compare the difference between those two means and say that when we have a distribution, a normally distributed variable, that the difference between those two means, the expected value of x, that mean that we expect from our sample, and the actual true mean can be written as this symbol here. And if you multiply that by the square root of n and divide by the standard deviation, that's the expected value, which means we can calculate our sample size based on a desired distribution, and we can adjust our confidence levels so that we know how many samples are required to get the power of the test that we want. And so these examples that you see here are the same thing that we saw for the power test previously in the chapter, but this time we're looking at the difference between the mean that they think we're supposed to have and the mean that we desire. And so in this case, we can identify the difference of those two means, multiply by the square root of the sample, divide by the standard deviation, and that z of alpha over 2, that z statistic for that gives us the probability of the type 2 error on a two-sided test, which means we can also manipulate that equation to find n. And this is the one that we're actually going to be focusing on most of the time. Most of the time, you're going to be saying, I know I want the test to have a certain power. Remember, we said power was 1 minus the type 2 error, and that said how robust the test was. So if I want to have a really robust test, and I want to ensure that my test is going to not have me falsely accept in a dangerous situation, like that product that we said was failing, I want to make sure that every time I collect a sample, I am rejecting all false positives. That means that I need to be able to know how many samples do I take to ensure that happens. And that's what we're looking at most of the time. So again, you have your z of alpha over 2 plus the z of your beta, that power, squared, times the standard deviation squared, which is actually the variance, and divided by the difference between the two means squared. And so again, that little symbol there is the difference between our two means, and for that we can estimate a sample size. We can also do that for a one-sided test where we use z of alpha instead of z of alpha over 2. And that's the only change in the formula. So we're going to look and say, what is the type 2 error? What is beta, which also will allow us to calculate power. But what is type 2 error for the problem that we just did? The true burning rate is 49 centimeters per second. Our alpha is 0.05, and our standard deviation is still 2. Our n is 25. And so we're going to find out what that error was. And so if I calculate this, I'm going to say that the difference between the two means is equal to that little funky symbol, and then mu minus mu naught, which in this case is equal to 50. That's what we were given, and 49, which is what the problem just said it actually is. And so the difference between those two is 1. We already know that our z of alpha over 2 is equal to 1.96, so we know what that is equal to. And so we're going to calculate the power beta by finding the probability of our test statistics. So that's z of alpha over 2, 1.96, minus the square root of 25, because that's our n, divided by the standard deviation, which was 2. And we're going to subtract that from the z statistic for negative 1.96, and subtract the square root of 25, which is our n, divided by the standard deviation, which was 2. And so beta is going to be equal to the z statistic of negative 0.54 minus the z statistic for negative 4.46. And so if we look these up in the table, we know that negative 0.54 is equal to 0.295, and the z-test statistic for negative 4.46 is 0. So that gives us a beta, a type 2 error of 0.295. So what does that mean? Well, that means that the power of this sample is actually equal to 1 minus beta. So that's 1 minus 0.295. And so you're looking at about 70%, right? Just over 70%, because we have 70.5%. Um, so 30% of the time, that test is going to fail to reject the null hypothesis when it should. So that's what this means. This means roughly 30% of the time, we are failing to reject that null hypothesis, um, even though the actual burning rate is 49, not 50. And so that, with understanding the error, gives us a reason to say, well, what should the actual sample size be? I want to know that I can have that. So instead of having a power of 70, what if I wanted a power of 90? So let's look at that. It says if we want to have the true mean differing by more than 1 centimeter per second, that we're going to test it, be able to detect that with a probability of 90. And so again, our ability to detect more than one, so that's 51 minus 50, and that's equal to 1. So that mean difference we're looking at is 1, right? So that as much of 1 centimeter per second. And we know that previously we were told that our alpha was equal to 0.05, but now we know what we want our beta to be. We want our beta to be equal to 0.10, because that's what we actually want to achieve. That's saying that we're going to be able to detect that with a high probability. And so that given probability of detection of that difference is 0.90. And so we know that beta is equal, that the power is equal to 1 minus beta. And so if I want the power to be 90, then beta is equal to 10%. So that's how we got that beta is equal to 10%. Our standard deviation is unchanged. And so now we're going to calculate what sort of sample is required so that I can actually detect this appropriately. And so my z of alpha over 2 is 1.96, as it has been all along. And now my z of beta, if I look that up on my z table, so for 0.1, my z of 0.1 is 1.28. And so this is z of 0.05 over 2, which is equal to 1.96, and z of 0.10 is equal to 1.28. So those are my z values. And now I'm going to be able to look at the formula here. And the formula was that n is equal to z of alpha over 2 plus z of beta squared times the standard deviation squared divided by the difference between the sample size and the mean squared. And so that is equal to 1.96 plus 1.28 squared multiplied by the standard deviation, 2 squared, divided by the difference between those means, 1 squared, and that is equal to a sample size of 42. So earlier, our problem told us that we were going to have 25 samples, and that only gave us a power of 70. Now, if we use a sample size of 42, we could guarantee that power of 90, that we would reject, as we should appropriately reject, that difference between means with a high probability, 90% of the time. And so you can see how we can use to calculate the power of the test if we know if we know what our actual n is, then we can calculate that power. If we don't know the n, or we want to calculate an n based on a certain power level, we can use this formula. So continuing, if we're going to look for a large sample, again, just as we did with chapter 8, when we have an n that is greater than 40, even if we don't know the variance, we can use a sample variance S as if it were sigma. That's for n greater than 40. But what about when n is less than 40? Well, we're going to use our t-table. And using our t-table, our null hypothesis is still going to be looking at that criteria like mu is equal to mu naught. Um, and our alternative hypothesis is still going to be looking at either a mu is not equal to mu naught, or a mu is less than, or a mu is greater than mu naught. All of those things stay the same, but our test statistic, instead of being the z, is now the t-table. And so that t-test statistic is the same we saw in chapter 8. It's x bar minus mu naught over s, the sample standard deviation, divided by the square root of n. And so we're going to use our t-values instead. And so when we compare the p-value, we're going to be comparing that given desired level of significance to the calculated t-value based on our sample. And so we're going to be looking for, on a two-sided test, we're going to be looking to see that t naught is greater than t of alpha over 2 n minus 1, or t naught is less than negative t alpha over 2 n minus 1, symmetry of the t curve. For our one-sided test, we'll be looking at that t statistic being greater than t of alpha n minus 1, or our test statistic less than t negative t of alpha n minus 1. Again, you have that symmetry of the t curve, just like we do for the z curve. And so when we're looking at this, we're going to calculate our p-value the same way we were calculating our p-value using the normal distribution, but now we're going to be using our t-table. And so we can do an example like that and look at, in your packet here, you should have a table that's just like the z table that we did, looking at a one sample t-test. And so in this case, we have 15 drivers of a particular club. So our n is equal to 15. So we're working with a small sample size. And we see that we're looking at an alpha of 0.05. And we're saying that they want to support a claim that the mean exceeds, the mean is greater than 0.82. The sample mean that was observed, x bar, is equal to 0.83725. 83725. So that sample mean was collected and the sample standard deviation is 0.02456. So based on that mean sample and that um, sample standard deviation and an n of 15, we're going to use our t. And so our null hypothesis is actually going to be that the mean is equal to 0.82, because our alternative hypothesis, the one that we're actually checking against, is that the mean is greater than 0.82. And so this means that we are doing a one-sided test. This whole greater than or less than, this means that we are doing a one-sided test. And so with a one-sided test, what we're going to be looking at is we're going to calculate our t-test statistic. And we know that that's equal to x bar minus mu naught divided by s over the square root of n. And so that gives us 0.83725 minus 0.82 divided by 0.02456 divided by the square root of 15. So that's our actual math to calculate our t-test statistic, and that is equal to 2.72. And so we're going to look at a t-distribution with 14 degrees of freedom, because remember, our degrees of freedom is equal to n minus 1. And so we're looking at 15 minus 1 equal to 14. And so we're going to look on our chart and just go across until you find a value that's close to 2.72. And we see that that actually falls between two values. If you look at an alpha of 0.01, you'll see that the t-test statistic is 2.624. And then the next one you see is an alpha of 0.005, and the t-test statistic is 2.977, which means our calculated test statistic falls in right there, somewhere between 0.01 and 0.055. So when you look at the difference between those, that means that our p value is between those. And so we can say that our specific p-value is between 0.005 and 0.01. No matter what, that means that our p is less than 0.05, which means we reject the null hypothesis. So in this case, we are saying that our p-value falls somewhere between these two levels. The t-table is much less specific, the one that's the PDF I gave you and the one in the textbook. Now, when we start using Minitab, Minitab will tell you exactly what the alpha is, your p-value given for any t-test statistic. It will give you the exact number. But in this case, we're looking at the book, and the book only gives us at these specific alpha levels. And so we know that this calculated test statistic, 2.72, is between 0.01 and 0.005. In either case, we are less than 0.05, and so we are going to reject HO. And so, um, we would say that the experiment in this case was a success. I will be doing another live Zoom on Thursday, and that will give you an opportunity to ask questions. We'll go through a few more examples again, which should help you as you go through the content for this work. And in the meantime, I wish you good health and hang in there as we're all in quarantine together. I look forward to virtually seeing you all on Thursday.